Okay, let's get started. Good afternoon. Today we are going to present achieving 10 million IOPS from single VM on Windows Hyper-V. I'm Liang. I'm from Microsoft Azure Performance team, and this is my perf buddy Danyu from Microsoft Windows Server Performance team. We have been together working on Hyper-V VM storage performance for probably more than 10 years, actually, since Hyper-V was born at Microsoft. Today's agenda is I will first cover some motivation and the performance challenges and the issues we solved. Also, we are going to review the Hyper-V storage paths and the optimization we have done. And Danyu is going to work with you performance configurations, settings, performance data, and the new NVMe polling model we have been doing on Windows. So if you attended today's morning session, Amber from Intel, actually, he described a very interesting story. She said, NVMe develops so fast, hardware develops so fast, performance becomes such incredible, but because of the software stack remains constant, almost constant, and the end user cannot really see the performance benefit brought by the hardware improvement. So as a software guy, I'm very sorry to hear that. And actually, that's the exact reason Danyu and I are working together to improve our software stack so we can bring the best performance experience to our customers. So you may ask, why 10 million IOPS? Why we need 10 million IOPS? So obviously, we have seen a strong customer demand for this high transaction-based workload, artificial intelligence, big data, machine learning, database, all this stuff. They want high throughput, all this high transaction-based. Also, cloud market growth. So you see all these cloud major vendors. They have seen this revenue doubled or even tripled year over year. So, and it's also a very competitive market. So every cloud vendor wanted to get the best performance VM SKUs to their customers. So obviously, we also wanted to have every VM SKU release has the high performance in terms of high throughput and low latencies. In the meantime, the hardware technologies during the past 10 years advanced very rapidly. That include now we have much faster storage today and a much more advanced processor today compared to like 10 years ago. In today's market, most of these cloud vendors has this called storage optimized VM SKUs. Amazon, Azure, Oracle, all these things. And all these VM SKUs could handle these IOPS at the millions IOPS levels. So let's first talk about the storage technology advancement which enables these high IOPS from storage perspective. We have attended several sessions that we talk about the shift from data center SSD storage interface from traditional SAS SATA to PCIe NVMe. Actually, interesting is the Seagate. People also discuss their thinking or planning move the HDD interface from traditional SAS SATA also to NVMe interface. So that's very interesting. And if you look at the table below, here we compared the theoretical protocol bandwidth and the actual IOPS between the SATA SSD, SAS SSD, and the PCIe NVMe SSDs. So SATA SSD, we know it's capped at like 600 megabytes. So in reality, the fast SATA SSD today delivers around 100K IOPS per device, even for enterprise skills. For 12 gig SAS, the theoretical bandwidth is like 1,200 megabytes per second. And in reality, today most top tier, this enterprise SAS SSD delivered around 250K IOPS, no more than that. But the PCIe NVMe SD, we are using this Gen 3, which is get very close to 4 gigabytes per second, and could deliver close to 1 million IOPS per second for PCIe by 4. So that's you see that's a huge jump compared to this traditional SATA and SAS SSDs in terms of performance. So let's first talk about this NVMe. NVMe, like Amber mentioned, is really designed from the ground up. So we can capitalize on high IOPS, low latency, based on these internal built-in parallelisms. What this internal built-in parallelism really means, if you look at this graph, we know traditionally, like SAS SATA, they only have a single command queues. But for NVMe, situation is quite different. They support large number of these I/O queues. Very common, we see like 32, 64, 128, or even 256 for in today's market. So that these multiple I/O queues can enable this device to scale their I/O initiation and completion with got a number of CPUs for high throughput. As a perfect guy, we really know actually if you look at this I/O path, most performance bottleneck come from either I/O completion or I/O initiation path. That's the two most important bottleneck for I/Os.
In the previous slide, you said that you have 1 million IOPS.
Yes.
The question is, are these reads or writes?
Reads.
Reads, and how big of an I/O are you talking about?
4K. Yeah, we said that all these IOPS is measured by 4K. Yeah. So obviously, we are talking about the 4K random reads. The write performance on this kind of NAND flash is it's not as good as reads. So let's spend some time to review Windows Hyper-V storage path. We know today Microsoft Azure is powered by Hyper-V. So all this VM stack actually is running based on top of Hyper-V. We have like 3 mode. This is very similar even for Linux world. Zen, KVM is very similar. We have emulation path that is engaged hypervisor constantly, so it's pretty slow. We also have this most frequently used is para-virtualized, or we call it synthetic path. So we use this enlightenment driver to bypass this hypervisor and minimize hypervisor involvement. And today we have this direct hardware assignment. That means we can access a PCIe device to a VM, that for best performance reasons. And from VM storage backend mode perspective, we also have this file-based. That is, for Hyper-V, we frequently use this virtual hard disk image, either VHD or VHDX. And that means for file-based, it means you have to sit on a file systems. So the file system has obvious overhead. So we also have like a physical disk based. That means we can bypass host file systems. So that includes SCSI pass-through, which means all this physical disk, is presented to the VM as a SCSI disk. And we also have these PCIe pass-throughs. Like we have this new feature in Windows Server 2016 to do this PCIe direct assignment. So that has better performance compared with this file-based mode. We wanted to review the storage performance work we have done during the past 10 years. First is our journey to mini IOPS VMs. It's very interesting. 6 years ago, we come here. We come to probably this same conference room. We announced that Hyper-V becomes the first hypervisor to achieve more than 1 mini IOPS from single VMs. So that's based on Windows Server 2012. A year later, in October 2013, Microsoft announced we achieved more than 2 mini IOPS from single VM. And we showed a public demo at the TechEd Europe 2013. So all these 1 mini IOPS, 2 mini IOPS demos, they all used similar configurations. It was based on 6.4 SCSI pass-through disk, I just mentioned. So that means they use traditional para-virtualized path. And every pass-through disk is backed by our SATA SSDs. So we just talked about the storage advanced very quickly. So now PCIe, a single PCIe Gen 3 by 4 can deliver close to 1 mini IOPS. And today, if you look at all these cloud vendors, for the best performance VM skills, they still heavily used local storage. So that will say, oh, we wanted to go beyond 1 minute, 2 minutes, 3 minute IOPS. So it's very natural work for us. But the experimental we have done actually showed the throughput within VM is going to be capped around the 3 minute IOPS if we continue using the traditional para-virtual path. And I'm going to explain next. So if you look at this graph, this is just the Hyper-V para-virtualized storage path. So on the left side, that's the VM side. You'll see we have some enablement driver. It's called a store VSC. Actually, we also have a Linux version, so that is already part of the Linux. So and then you cross the boundary VM bus driver, we will set it down on the host. We have the store VSP driver, then we go through some parcels, then we send it to the I/O disk, physical disk. So look at this graph. Every storage I/O goes through the I/O initiation and the completion path twice. Once in the VM, and another one we have to do it the same again on host. Also, you will notice that the contention between the root virtual processors and the VM virtual processors is going to present a very big performance bottlenecks. Because you have host stack, you have the VM stack, they will contend for CPU cycles. We have some existing mitigations. We have Hyper-V main root, we have a CPU group. What these features do is they just isolate these root VPs from VM virtual processors, so they will not contend with each other. Like I said, we found this Hyper-V VM is going to cap it at the 3 minute IOPS based on traditional para-virtual path. So where this overhead come from? We did some experiment. So if you look at this table here, this is the Windows Hyper-V storage path CPU overhead breakdown. A caveat here is was measured using 1 minute IOPS traffic, 4K random reads. So the data may be different depending on OS or the traffic, but generally they match or scales linearly. So if you look at this one, the first one is the guest component overhead. That's roughly like 20%. And this overhead comes from Hyper-V guest enablement, as we said, store VSC here. This enablement is made aware, oh, I'm running in a virtualization environment. So obviously we have a guest OS storage stack because the VM is also OS. So combining them together, the guest storage stack took 20% CPU cycles away. Now we just mentioned that every I/O has to cross the boundary from VM to host, and then come back from host to VM. And across the boundary, we use this shared buffer mechanism. That's use the VM bus. And that also take away 20% CPU cycles. Of course, the biggest part comes from the host. The first one is we have Hyper-V host component. We just mentioned we have the store VSP driver that is mainly responsible for our dispatching purpose. We also have that parcel, like VHDMP parcels for like a file-based image. So we mentioned for this file-based, we have host file system overhead, NTFS, for example. So that's roughly 10%. Of course, host the storage stack. That means the disk driver, your store port, mini port. That is about 10%. So you put all this together, the host take away 40% CPU cycles. Another one is, of course, the hypervisor. So that is, under this 1 minute IOPS, is about 20% overhead. And for most of this 20% overhead, the interrupt delivery is the dominant. So we are going to explain more how we mitigate this both. So obviously, this table shows us CPU cost is typically a bottleneck for these high IOPS, for this mini IOPS or over mini IOPS workload. So we wanted to mitigate. We wanted to save CPU cycle as much as possible. So there are two different directions. The new storage virtualization technologies that will help mitigate host as well as VM to host overhead. That's the storage virtualization part. And another part is new processor IO virtualization technologies like APIC V or post-interrupt. That's going to help mitigate hypervisor overhead dealing with interrupt delivery to virtual processors.
Could you please elaborate once again what those values overhead means?
Means the CPU cycles. So like you say, for example, Skylake CPU, right? So it's like a 2.7 gigahertz. So how many CPU cycles you're going to spend for these IOs? So generally, you do the calculation. You divide it by your total CPU cycles per second, divided by your IO per second. So you get for every IO, you get how many CPU cycles you consumed.
On the left-hand side, it's also breakdown in terms of CPU cycles, right?
Yes.
Okay.
Yeah. So that's roughly how we get these calculations.
Okay, and they roughly match. So 15 plus 5, okay. In the lowest row, there is a...
Yeah. So traditional para-virtualized has this kind of inherent overhead. And because it cannot avoid this kind of contention, root VP, VM VP, so traditional hyperviscosity pass-through is not sufficient to provide maximum performance. Now you will ask, hey, a natural response is why we shift to the storage SLVs. Yes, storage SLV today is still not there yet. Just like Amber mentioned in today's sessions, in NVMe spec, we do have these virtualization enhancement sections dealing with the SLV support. But there's some key part is not there yet. For example, lack of resource control. How to get rid of the noisy labeling issues. So if you have multiple VMs, or you don't want one VM doing 4K random writes, another VM is doing 4K random reads, that the VM user doing 4K random reads is going to suffer significantly because of this another VM is doing this 4K random writes. So we did some kind of a resource control mechanism in NVMe spec to handle this kind of stuff. And that one is not there yet today. Also, if you look at the different SSD hardware vendors, they all come up with their own implementations. They're trying to make up some missing details for themselves. I can give you a few examples. I don't want to name the name, but I see different SSD vendors, they have quite a different implementation. Say how many virtual functions. Most of them just choose the fixed number of virtual functions. But from a cloud vendor perspective, they want a flexible. We want to 16, 32, or even 8. So that kind of implementation today is not available in industry. So all this make the software stack support SLVs really difficult. That's the reality. So we talk about the Hyper-V discrete device assignment. That's a PCIe pass-through technologies. So essentially, we can assign a PCIe device directly to a VM. So this is still an experimental feature. We first introduced in Windows Server 2016. This feature always has performance benefit because it allows VM user to access these IO queues directly. That brings a significant performance gain compared with traditional para-virtualized paths. But it has very serious security concerns because a malicious VM, by exposing admin queue to VM user, a malicious VM user could do something pretty bad. And that could make your host and other VM running on the same host suffer. So that's the reason this remains an experimental feature for DDA part. So we want a secured direct storage hardware access solution in cloud VM. Obviously, PCIe NVMe is best suited for this purpose. And how to do that, how to make it safe. So we did field out this unsafe admin command. Well, we still allow this VM user to access IOQ directly. So I'm just talking about this solution generally. If I have some questions, I'll refer you to some internet announcement just this week. So software solution, we can do it either at the hypervisor layer or we can use like a dedicated host field driver to intercept this kind of admin request. And we can take actions accordingly. And another one is also very common, is hardware solution. People can use FPGA or customize ASIC to filter this unsafe admin command. And the other solutions, like for example, the BMC, we can only dedicate this risk device management, like a firmware update, through BMC or PLDM only. So that's something interesting. But
Can you explain a little bit about what you're looking for here? As far as, say there was a customized solution, the idea is that you would not want any admin commands to be able to be processed while there is virtual I/O commands that are being done?
so basically, the hardware solution and software solution is largely doing the same thing. So you can refer to Amazon natural architecture. So I'm from Microsoft, but the principle is the same. What the hardware does is they exposed a fake NVMe device to VMs. So every admin command actually is first intercepted by this either hardware or software. So if it's like a firmware update command, they will just probably cancel it.
So this assumes that you don't have like an SRIOP solution.
No.
This is if you're using that.
Exactly. That's I mentioned today. Storage SLV is not there yet. And then we need a solution now for best performance.
But it assumes using direct assignment, so you're assigning the entire PCIe device.
Yes. Yes. We are not partitioning anything. We just assign entire device to VM.
But still you want to access admin queue
Yes.
from hypervisor.
Yes. Yes.
And
We just I can go a little bit of detail because everything is mapped like a page, right? So you can just intercept this page request. Then you can say, oh, it's the main queue. We just kill it.
don't you need to recalculate DRP addresses?
You don't need to. You don't need to. You don't need to. Yeah.
Can you give me an example of an unsafe NVMe?
Yeah. Firmware update.
Firmware update?
Firmware update. Yes. You definitely don't want a malicious user to do this firmware update. Who knows security concerns?
So you're saying that you got to be offline to do firmware update?
You don't want them do this. Yeah.
You need to be sending the firmware update not from the guest OS.
Exactly.
The key is that without a mechanism to separate out what's the guest and which one is the actual physical.
Exactly. Yeah. So that's, yeah.
Is there a way to lock up the admin queue for certain commands such that it will execute?
No, that's not available. Yeah. We have some consider we expand the doorbell registers, but today every vendor, it's very interesting. The spec support a customized doorbell strategy size, but in reality, every vendor they just zero gap, so we can't do that. Otherwise, we just separate the admin doorbell into a different page, then issue is solved, but we can't. Okay, so we talk about the storage overhead. Let's pause a moment and review this interrupt. I just mentioned the hypervisor overhead. Most of hypervisor overhead is dealing the interrupt delivery. So we know actually in a virtualization environment, deliver interrupt to a VM is much more expensive than in a bare metal environment. And the reason is we have this VM exit overhead. So all means in hypervisor intercept. So during a virtual interrupt delivery, we need to frequently suspend your VM and exit to hypervisor to update some data structure and then come back, resume that VM. So for example, there are several most typical type of this overhead come from. First one is APIC register access. So we have several very common interrupt, request register, interrupt command register, or end of interrupt register. So if you want to generate the interrupt, or you want to deliver interrupt, or you want signaling complete the interrupt, you need to write MSR registers. And this kind of update registers cause a VM exit or hypervisor intercept. Another one is like EP, interprocessor interrupt. That makes things worse because on the sending virtual processor and the receiving virtual processor, they both need to exit. And on the right part, that is when external device, like I/O device, generate this interrupt. That goes through LMMU, goes through hypervisor, and finally deliver to these virtual processors. That will also go to this VM exit. So we copy paste of Windows Hyper-V virtual processor performance count here just to show you how big this hypervisor intercept overhead could become. So this was measured under like a 4.5 milliamps traffic. So if you look at the hypervisor runtime CPU, that's 20%. So that means the hypervisor dealing with all these interrupt related hypervisor intercept takes 20% total CPU time out. And the total intercept for 4.1 milliamps traffic is 9.2 millions per second hypervisor intercept. You can see how hypervisor is busy. So hardware interrupt is 2.2. Obviously, we have some kind of interrupt coalescing mechanism here. So that is for 2 IOs, we have 1 interrupt here. But overall, this performance counter we used here just to show for this IO intensive workload how expensive dealing with interrupt delivery will become. So that's the issue we have to solve. So virtual interrupt delivery overhead actually is a well-known issue to industry. So both Intel and AMD, they're working very hard to solve this or mitigate this. If you look at the Intel server processor roadmap from New Helen, Everbridge, Haswell, Broadwell to Skylake. So a peak virtualization is available starting from the Everbridge. And the post-interrupt support made available from Broadwell. For AMD, from Barcelona to Bulldozer to the latest EPYC, that's based on Zen microarchitecture. AVIC support was made available on EPYC. So I will briefly just go through this Intel one. I don't want to go to much details here. So Intel virtualization technology advancement include 2 parts. We just saw that we wanted to mitigate the issue related to the peak register access. Also, we wanted to mitigate the access with interrupt delivery. So Intel has this peak virtualization that allows guests to directly access peak register from virtual peak page. So you don't incur VM exit. And the post-interrupt actually was made in Zen a while ago, but for Windows, it's still new. So post-interrupt enables this direct external interrupt delivery to VM VPs with reduced hypervisor involvement. We choose the term reduced is because this does not get rid of this VM exit completely. For example, on EP, on the sending CPU, we still need the VM exit for security concerns. So we worked at Microsoft, Danyu and I worked with this Hyper-V team and other teams to enable this both post-PI, PI support and IPv support starting from Windows Server 2019. So that was announced this week. AMD has very similar technology, also with different implementation. So it's called AVIC. That's the term AMD used for APIC-V. So that AVIC, although most APIC access and the interrupt delivery into guest, also with reduced VM exit. So one thing we need to remind you here is because they have different implementation. So for post-interrupt support on AMD platforms, they use different mechanisms. They have to update a data structure called guest virtual APIC, GA logging table constantly. So the experiment Danyu and I did uncover this for very high IOPS traffic. These GA logging mechanisms could incur also very significant performance overhead. So, but this is just tied to AMD implementation. So with that, I'm going to hand over to Danyu. He's going to walk through with you the rest of the sections.
Okay, thanks, Liang, for a great overview of the past 10-20 years of the storage advancement and I/O virtualization advancement. So this is the foundation of our work to deliver 10 million IOPS platform. Without that, it is impossible for our work. So this slide shows 2 tables. The first table shows the system machine configurations. So what kind of machines, what kind of storage of systems we use to build up this platform. The lower table shows the virtual machine configuration. So first one for the systems, we're using a commodity HP DL560 Gen 10 server. This is commodity server, you can buy it from the market. So this is a 4-socket server with the Intel Skylake 8168 processors. Overall, the 4-socket server processors deliver 192 logical processors at 2.7 GHz. So these processors, this number of processors provide enough CPU powers to deliver the 10 million IOPS that we needed. For the storage subsystems, we're using Intel PCIe Gen 3 half-length AIC P4608 NVMe devices. So this NVMe form factor has a very interesting design. They kind of stack 2 NVMe SSDs into one form factor, so that on one form factor it can deliver 1.4 million IOPS. So that we can save the PCIe slot only using 8 PCIe Gen 3 by 8 to deliver this kind of IOPS. So with that, you can see that on the hardware side, we have all the powers to deliver more than 10 million IOPS on theory. Now let's look at the virtual machines. So we are using we create a VM with 192 virtual processors. So the reason we are creating this four-size VM is for fair comparison between the bare metal, root, and VM. So that we have same size of the machines, so we can see how much we can get on the I/O side. We enable virtual NUMA in the VM so that they can better map the devices into the NUMA topology. The host OS and the guest OS both using Windows Server 2019 with all optimizations and features we delivered on this new platform. Now this slide shows the test tools and experiment settings we use to deliver for this I/O benchmarking. Now I know FIO is very popular in this world, but on Windows side we have a tool called DiskSpeed. That is also open source. That's all the source code and binaries are on the GitHub. So if you want, you can download the source code to build yourself. So this tool is using all Windows APIs. So the more close to what the customer will use in the real world. Actually, tomorrow, one of my colleagues, Danyu, also coming from Windows Server team, he is going to have a talk on DiskSpeed, talk about how these tools advanced. He is going to get some demos, how to use these tools, and all the new features delivered there. So I recommend people to go to that talk as well. For the experiment settings, we use each NVMe device as a raw disk, using raw IOs, and also using NTFS file systems in the middle. We're using one disk speed for every disk. Every disk we're using 8 IO queues, affinitized to 8 VM VPs. And we use 128 queue depths per thread. Overall, every SSD is 1024 queue depths. So these queue depths is enough to drive the physical capacity of the SSDs. We're using 4K random rate aligned to 4K boundaries. This is non-buffered IO, it's not buffered IO. So it's actually go to all disks. For the performance comparisons, we compare 3 different configurations. We compare bare metal and the root. Basically, you have direct access to the hardware and also the VM. So we see how it looks like in the next slide. So here is the performance results we deliver on these platforms. One thing I want to mention here is that we are using the traditional interrupt mode on the NVMe driver. So this means all IOs is delivered by interrupt mode. In the next few slides, I'm going to talk about another different experiment mode we introduced on 2019 on the pooling mode to see how the comparison of interrupt mode and the pooling mode in the next few slides. But here, all the results is delivered on the traditional NVMe interrupt mode. On the x-axis, there's 6 different configurations we tried, and Y is the I/O throughput that is delivered. So the first one is this is bare metal. You can see that on bare metal, we can deliver 11 milliamps on this platform. So it's really good, 11 milliamps. But now, if we move to the VM, that's in the para-virtualized select path, traditionally in the VM, 192 VMs, very large VM with all the CPUs, we dropped from 11 milliamps down to 2.5 milliamps. So we only use a fraction of the hardware power here. As Liang mentioned just earlier, that we do the experiment, we try different configurations, try different tweakings. No matter how we try it, it cannot beyond 3 milliamps. So this is the gap, very big gap here. Now, how about we move to the root? So the root here have all access about the direct access to the hardware. Now, interesting enough, we only deliver 7.2 milliamps. The reason for that, as Liang mentioned earlier, is that on the root, even the OS has direct access to hardware, the interrupt delivery still have a huge overhead. So this is the one without post-interrupt support. That's on 2016. We haven't enabled the post-interrupt support yet. Now, if we move to the VM with DDA, direct discrete access, so that the throughput further drop from 7.2 million to 4.5 million. The reason for this drop is that on the root, you have a one-to-one VP to logic processors mappings. But on the guest VM, you don't have that mappings. Let's introduce some additional overhead on the hypervisor. For example, one example is that you have to grab a partition lock when you do the interprocessor delivery, interrupt delivery. And another example is that when there's a API query performance counters, that become syscall instead of the user mode API. So we did some optimizations in the 2019 on hypervisor level to get rid of some of the overhead, try to minimize that. So the last two rows shows that we have all optimizations on the 2019. This is the root with post-interrupt enabled. Now the throughput increased from 7.2 million to 10 million. It's fairly close to what the bare metal can deliver. It's only a fraction, less than 10% difference. Now, most interesting part is on the last one. In the VM, we can deliver exactly the same throughput as root. That's 10 million IOPS from a single VM. So that's a very, very amazing number that we achieved from a single VM today. Now let's talk about another mode, NVMe pooling. So we see all the platform can do very good performance on this interrupt mode. So why we consider pooling? So the main reason for pooling is that it will help VM to achieve those close to bare metal performance on the platforms that doesn't have those efficient EIP post-interrupt support. So as I mentioned, that not every platform has the post-interrupt support. That if we don't have that, it means you have very high interrupt delivery overhead. Now with pooling, constant pooling, there's no interrupt, you can eliminate all the interrupt overhead. And there's another reason for that is that some NVMe devices, they don't have enough I/O queues. So that means they don't have enough MSIX interrupts. Now, if, for example, you have only 8 MSI interrupts, but you have 192 virtual processors in the VM, you become coming into the how to balance those interrupts into virtual processors. You can easily come into these mapping problems. So we have seen in the reality that these become a very big performance concerns in the virtualized environment. Let's capture the throughput to a very large scale. Now, if you compare pooling with interrupt, pooling, of course, provides much lower latencies and more consistent I/O tail latencies. You don't need to wait I/O completions coming into the VM and then go to the DPCs and go to the I/O completions. You constantly pooling the completion queues, so they get very low latencies. But of course, on the other hand, you are going to incur a little bit some higher CPU costs if the queue depth is pretty low for those low queue depth workloads. So there's a balance here. On the Linux world, the pooling has already introduced on kernel 4.4. That's a while back. On 4.10, there's already a hybrid pooling mode introduced on Linux world. But the Windows is far behind. So far, none of the Windows drivers support pooling mode. Not the inbox driver, not third-party drivers. We just don't have that available today. So Liang and I have working with other people in the Microsoft. We experimented some pooling support by modifying the current NVMe drivers on Windows 2019. So we see how it looks like. So before I go to the results, I want to present a little bit deeper on how we implement this NVMe pooling on the Windows side. Now if you look at this graph, this is a very simplified graph of the pooling implementations on our side. So you have a user app, you send IO initiations to the submission queues. Then on the NVMe driver side, it's going to queue the pooling DPCs and constantly pull the IO completion queues. Then it will continue to pull the IO completion queues until it found there is no pending IO exists. So it will leave these pooling queues. So a few points over here. The first one, the interrupt is disabled for every pooling mode queue. And we also support a mix of the pooling queues of the pooling queues, interrupt queues, so that you can interrupts still make sense for some of the large IOs. You don't want constant pooling for one big IO, for example. So that's we support mode. You can split the IO completion queues into two modes. Some of them you can configure in the pooling queues, some can be interrupt queues. So that you can get benefit from all of that. The third one is there's two modes in Windows, traditional DPC mode or thread DPC mode. By default, we're using thread DPC mode, so the system can be more responsive. And there's a passive level DPC, all other interrupt can come in. And the DPC is scheduled to all IO initiating processors. So if your applications is scaled out of all the processors, you get DPC scaled out nicely along with DPCs. So we have more balanced CPU usage. And another one is that we don't have dedicated pooling thread. We queue DPCs when there is alternate IOs. If there's no alternate IOs, there's no pooling cost. So that's one of nice design on this one. So these are the results we got on this platform, particular platform. So this is the bare metal on interrupt mode. Now, if we enable the interrupt pooling mode, we increase about 10% to 12 milliamps. And the one thing I want to mention here is that this platform has very efficient post-interrupt support. So that's why you did not see a lot of improvements on this platform. But even on that, you can see more than 10% improvements, throughput improvements. On the VM side, we improved from 10 milliamps to 11 milliamps. But Liang and I have done some experiments on other platforms that don't have efficient post-interrupt support, and also the NVMe devices have limited I/O queues. On that platform, we have seen a huge improvements because of the benefit we just talked about earlier. Now, for the conclusions on this one, there's a few points Liang and I want to make. The first one is I/O optimized skills is very critical for all the cloud providers. We saw the very strong customer demands, and also all the cloud providers are starting to provide those I/O optimized skills, 3 million, 4 million. So that's the one that the customer wants, actually wants. And with that demand, the traditional para-virtualized path apparently cannot meet the need. It's already hit the performance limit. It cannot go anywhere with the para-virtualized path. Then we need the direct device assignment that can bypass all the para-virtualized overhead and also the latest I/O virtualization enhancement there. Those are both the keys to achieve the near native performance for within VM. So as Amber mentioned this earlier, the software is evil right now. So we have still a long journey to go to reduce the overhead. This is just the start of the whole journey. Now, last one is the Windows Hyper-V stack can provide 10 million IOPS from a single VM. So we are doing that on a modern commodity hardware. Now, we really want to thank Intel and HP. They are generous support for this work. They provide the hardware and SSDs, and without their support, that's impossible for us to complete the work. So that platform is really, really expensive. So, any questions?
Okay. Okay, thank you everyone.